You get an A for the day. That's not going to get you anywhere, by the way, but it gets you an A for the day. So you can go home and you can tell your friends, you can tell your family, you can say, hey, I made an A for the day in biochemistry today. Pretty good, huh? First week is done. Survive 1 week of biochemistry. Survive 1 week of me. 1 week of me singing songs to you. Hopefully that's not too painful. We've got some things to do. As you're starting to see, I go through things reasonably fast. And so there's a lot of material to cover. So that's important to do. The good news is that hopefully it all makes sense. So if you're having questions or having problems or things you aren't understanding, the best time to catch me is now. Okay? Because the closer to exam time it gets, the harder it is because everybody starts crowding my office and so forth. And so I want to make sure I've got connection with you. I do have 2 TAs for the class, and they will be, in fact, I haven't posted their office hours yet, but I will post their office hours. We also have something that we started earlier this year that has been very popular with students. It is a free set of help sessions for anybody studying biochemistry. They occur on Monday, Tuesday, Wednesday, Thursday evenings from 6 to 8. And they're located in ALS 2018. It's called the Major Groove. What you will find there are biochemistry majors who are there to answer questions about any aspect of biochemistry that you may have. So they've all had biochemistry, they've all done very well in biochemistry, and they're interested in helping you to understand more about biochemistry as well. So as I said, Major Groove, Monday, Tuesday, Wednesday, Thursday from 6 to 8 p.m. in ALS 2018. I hope that you will use it. And one of the reasons I hope that you will use it is that these are maintained basically by popularity. So if people don't come and use them, or they only use them, let's say, the night before an exam, then the likelihood it's going to be there for the next exam goes down. You know, so the idea of these is to help you as you're going along to understand things. So please take advantage of them if there's anything that you can do. I can always, or any help that you need. I can always help you to find tutors and things like that, but as I tell students, this is free tutoring with people who are experts in the area. If you want additional tutoring or something, then of course let me know, and I'll be happy to help connect you. Okay, well, let's dive into the subject of amino acids and proteins. You saw a little bit last time about how we got started in that, and I'm going to flesh that out for you a little bit more. As you've been seeing, my songs tend to be a little bit ahead of the lectures at this point in the term. I do try to sing a song every day. So I've got a whole bunch of songs, so hopefully I'll have something for you every day. Some days I get a little tied up and I don't get a song in, but I will try to get a song for you every day. And yes, I do have one for today as well. Amino acids are, as I said last time, the building blocks of proteins. And there are 20 amino acids that are commonly found in proteins. After the last lecture, I went back and I added the structures of all these, not because I'm expecting you to memorize the structure, but you can get an idea about, you know, what some of these things actually look like. This is one I frequently point students to that we'll talk about because it's big. Okay, it's the biggest amino acid. It's very large, and you don't need to memorize that or anything. But the point is that there are some things about structure that are going to be sort of recurring themes, and this one is one that has a recurring theme that we'll see. First of all, let me orient you on this molecule to what I talked about last time. If you recall, I said that every amino acid has an alpha carboxyl, and the alpha carboxyl is right there. A carboxyl, of course, has a double bonded oxygen and an OH bonded to a carbon, so that makes it a carboxyl. Every amino acid has an alpha amino group, and there's the alpha amino group right there. Every amino acid has an alpha carbon group, and that's the alpha carbon group right there. And it's called the alpha carbon because the alpha carboxyl and the alpha amine are attached to it. And every amino acid has an R group. And you can see that the R group here is pretty good sized. It's the R group through which amino acids differ from each other. Some amino acids have very large R groups, and this is a pretty large one right here. Some have very small R groups. So if we look at tryptophan, that's what it looks like. If by contrast I go to glycine and look at it, you'll see that its R group is basically a hydrogen. That's why it's not even shown as a sticking thing there. You've got alpha carbon, alpha amine, carboxyl, and you've got 2 hydrogens sticking off of this thing. Okay? So R groups can be very tiny in the case of glycine. They can be very large, as in the case of tryptophan. They can also, in some cases, have things that get charged. So if we look, for example, at aspartic acid, we see aspartic acid, okay, to orient you, there's the alpha carboxyl, there's the alpha amine, there's the alpha carbon, and now the R group has another carboxyl group in it. Well, carboxyl groups can always ionize, meaning they can lose or gain a proton. This guy already has a proton on, so it can lose a proton. And if it loses a proton, it's going to become negatively charged. So one of the things that I told you was that I wasn't going to make you memorize structures of amino acids, and I'm not, but you should know which amino acids have R groups that will ionize. Okay? So how do you tell those? Well, I'll show you right here. If it says acidic, it has an R group that is a carboxyl, meaning that it can lose a proton and become negatively charged. That's one that can ionize. The other that can ionize for our purposes are those that are labeled basic. And if we take a look at them, we will see, in the case of lysine, there's the alpha carboxyl, there's the alpha carbon, there's the alpha amine. We see that it has an extra NH3 group on it. In this case, the NH3 group has a proton on it, and you can see that it's positively charged. If it loses that proton, it will have a charge of 0. All of the amino acids labeled basic have an R group that has an amine in it, meaning it can gain a proton and become positively charged, lose a proton, and become 0 charged. Okay? So there's really 5 amino acids that you should know that they ionize in their R groups and how they ionize in their R groups. Okay? The ones that are labeled basic have amines. Those amines can be either +1 or 0. The ones that are labeled acidic have carboxyls, and they can either have a charge of 0 when the proton is on or a negative when the proton is off. Now, I'm not going to ask you to draw those, but you should know those charges because, as we're going to see, one of the things you're going to have to be able to do is predict the charge on proteins that contain those. Okay? You're going to have to predict the charge of proteins that contain those. So in order for you to know those things, you will have to know, oh, this is a histidine. A histidine is a basic amino acid. It has an amine out there. It can gain or lose a proton. If it gains a proton, it's a +1. If it loses a proton, it's a charge of 0. And I'm going to show you how you make that determination, whether it gains or loses a proton. I'll show you that today. Okay? Everybody with me? Everybody understand that? Okay. So, not making you memorize the structures, but you should definitely know how these things become charged. All right. Well, as I said, there's a whole bunch of different amino acids that are out there, and they differ only in the structure of their R groups. There's a couple of them I want to make some note of. So I've shown you tryptophan, big, bulky R group. One of the things we see about a protein is a polymer of amino acids, and those R groups are just kind of hanging out there in space. And because those R groups for things like tryptophan are very large, they place constraints on the shape of a molecule that contains them. So I want you to just plant that idea in the back of your mind. I'll talk more about that later. But something that's got a big R group is going to have bulkiness associated with it. And something that's got a very tiny R group is going to have much more flexibility in terms of structure. So we could imagine that a protein that contains glycine is going to have more flexibility because its R group is a hydrogen, very tiny. And something that contains tryptophan is going to have a bulky R group, and it's not going to have as much flexibility. Another one that we have to consider in terms of flexibility is this amino acid called proline. And where's my proline here? There we go. Yes, thank you. I forget where my organization is. Okay, proline is the only one that has an R group where it's attached to the alpha carbon. It's attached to the alpha carbon, okay? I'm sorry, it's attached to the alpha amine. I said alpha carbon. So here is proline. There's the alpha carbon. There is the carboxyl. There is the alpha amine, but the alpha amine is attached to the R group. It's the only one that has that property. Now, proline actually ends up being a very interesting amino acid because of that, because as we're going to see, the alpha amine is involved in the formation of peptide bonds, the things that hold proteins together. And proline turns out to be the least flexible of all of the amino acids because it's got this attachment to the alpha amine group. I'll show you that in a little bit. That has some very interesting implications. Okay? Very interesting implications. All right. Let's see, what else did I want to say here? So I've shown you the acidic, I've shown you the basic, I've shown you how they ionize. I've shown you those that have a small R group, like glycine. Those that have a big R group, like tryptophan. Okay? And there's a couple more I want to point out. And by the way, I should point out when you look in books, you'll see that these things get classified slightly differently by different books or by different people. Okay? Classifications are merely that, just ways of organizing things. Don't get hung up by different classification systems that different people use. Okay? If you know the classification system I give you, that's all you'll need to know in this class. Okay? You'll need to know my classification system. Don't worry about others. All right. Well, there's a couple of interesting amino acids besides the ones I've shown you. One is methionine. Methionine is one of two amino acids that contains sulfur. Sulfur is an essential nutrient for you. And the reason it's an essential nutrient is you need to be able to make methionine and the other amino acid that contains sulfur, which is cysteine, that I'll show you in just a second. Methionine is interesting because when we go to talk later about how proteins get made, methionine turns out to almost always be the first amino acid that's made in a protein. When we go putting the amino acids together, the first one that goes into almost every protein on the face of the earth, almost every one starts with a methionine. Now, the sulfur that's in methionine is very unreactive. Okay? By comparison to the sulfur that's in cysteine, the one that's in methionine is not very reactive at all. Okay? It just sits there and does its thing. And we'll talk later in the term about one reaction that this methionine sulfur does go through, but for the most part, it doesn't react very much at all. Okay? One of the reactions that we'll talk about later in the term that methionine's sulfur goes through is something that affects and causes lung cancer. We'll talk about that later. But with the exception of that one, we don't really have much that happens with this sulfur in methionine. Okay. The other amino acid that contains sulfur has a much more reactive sulfur, and it's called cysteine. The sulfur that's in cysteine is attached on one side to a carbon and on the other side to a hydrogen. It makes what we call a sulfhydryl bond. S-U-L-F-H-Y-D-R-Y-L. And if I'm spelling for it spelling it for you, you can imagine that that's going to be important for you to know how to spell. Okay? Sulfhydryl bond. So an SH bond is a sulfhydryl bond. Sulfhydryl bonds are fairly reactive. That sulfur that's there can interact with another sulfur in another sulfhydryl, and the two sulfurs can end up being joined to each other. So imagine I had a cysteine over here on the top, and I had another cysteine down here, and the two sulfhydryls started butting heads. Well, when the two sulfhydryls butt heads, the hydrogens will disappear, and the two sulfurs will end up joined to each other. That's called a disulfide bond. And that's a covalent bond, and that's a very strong bond. Now, that will become important when we talk about things that help to stabilize the structure of a protein. Cysteines within a protein, if they get close to each other, will actually have the reaction that I just described to you. You'll make disulfide bonds, and that will help, in many cases, to stabilize the structure of a protein. Everybody understand? Okay. So the sulfur that's in cysteine is very different in terms of reactivity than the sulfur that's in methionine. Okay. Questions? Yes? Sulfhydryl? Yes. S-U-L-F-H-Y-D-R-Y-L. Sulfhydryl. Okay? Other questions? Okay. So those, in summary, in very brief summary, are the amino acids. I would encourage you to just look through them. Not that you're going to draw them or anything like that, but look through them and you get a feel for the diversity of the 20 amino acids that are there. Okay? All right. Now, let's see. Amino acids have abbreviations, et cetera, and the good news is I don't make you memorize them. Okay? I don't make you memorize them. You are welcome in this class to use any abbreviation that I use, as long as it's exact as the abbreviation I use. Okay? You can use any of the abbreviations here if you want. Okay? But again, they have to be exact. The safer thing is to use the actual name. And when I give you things, I will give it to you as the actual name. I'm not going to give it to you as the abbreviation so that you have to go, oh my God, what was HIS again? I don't remember what that was. All right? You'll see they have both 3-letter codes and 1-letter codes, and the 1-letter codes are even harder to remember than the 3-letter codes are, so why bother, right? If you know what they are, that's the most important thing. And remember, you do need to know the names of the 20 amino acids. And no, I'm not going to say list the 20 amino acids. Okay? But if I tell you cysteine, I would hope that you, if I use the word cysteine, I would hope you know that's an amino acid. Or I use tyrosine, you would know that's an amino acid. Okay? Okay. There are some unusual amino acids that we find in proteins. And I said there's 20, and now all of a sudden I'm going to show you some other ones that are there. The other ones that we find in proteins are actually there not because they're put into proteins in that way, but rather they're put in as a given structure, and then they're modified. So you can see, for example, hydroxyproline. Hydroxyproline is put into a protein as proline, and then it later gets modified by putting a hydroxyl group on it. So it never exists in the cell as just hydroxyproline. Makes sense? So we're modifying the amino acids in some cases after they get put into proteins. Hydroxyproline turns out to be a very interesting one that we'll talk about, I think, on Monday. I think it's on Monday I talk about that. Because hydroxyproline turns out to be a component of the most abundant protein in your body. Okay? Anybody want to fathom a guess as to what the most abundant protein in your body is? Collagen. Who said that? Back there. Very good. Collagen is the most abundant protein in your body. It is literally the glue that sticks you together. Okay? Collagen has some very interesting structure, and one of the components of its structure is this amino acid, I can't talk today, called hydroxyproline. Okay? The hydroxy group on hydroxyproline gets onto proline as a result of a reaction that requires vitamin C. The reason that you have to have vitamin C is so that you can make hydroxyproline within collagen. Now that turns out to be really cool and really interesting. I'll talk about it later, but suffice it to say that that reaction requires vitamin C and is one of the primary reasons you have to have vitamin C in your diet. You can't make vitamin C. Okay? If you're a rat, you can. Rats can make vitamin C, and there are some people who are rats, but we don't want to talk about them. But that's it. Somebody laughed at my joke. This is good. Okay. Some people are rats, but they can't make vitamin C either. Only the real live rats can do that. Okay. Hydroxylysine is another one that we see on occasion. We see it in collagen as well. Okay. And the last one is thyroxine. Anybody know where we see this one? Its name gives you a hint. What was that? Yeah, it's a thyroid hormone. You find it in thyroid gland hormone. Okay. So that's where thyroxine is found. And thyroid, for the thyroid gland, you might recall you need iodine as a nutrient. And look at all the I's on there. Okay? That's why you need iodine in your diet, so that you can make thyroid hormone. Okay. Blah, blah. Let's see. There are some things that are made from amino acids. And I'm just going to mention them to you again. Don't worry about structure. You see the parent amino acid at the very top, which is tryptophan. And from tryptophan, we can make a couple of interesting things. One is hydroxytryptophan, which is an intermediate and the way to making serotonin. Okay? Serotonin, some people associate with sleeping. And there are people, for example, who think that if you eat a lot of turkey on Thanksgiving Day, what you're getting is a lot of tryptophan, and the reason you want to take a nap after that giant turkey dinner is because your body's making a lot of serotonin and you're going to sleep. Some people argue with that, but that may or may not be the case. But this is a compound that's made from the amino acid known as tryptophan. Okay? Dopamine and epinephrine are two others. They're actually made from tyrosine. Dopamine is what's called a neurotransmitter. It's necessary for one nerve cell to talk to another nerve cell to communicate a signal. People who have Parkinson's disease, for example, have trouble with making that neurotransmitter or getting that signal communicated across that neurotransmitter junction. So dopamine is the compound that's necessary to do that. One of the ways that they treat, in fact, treating Parkinson's is very, very difficult to do because you have a blood-brain barrier, and getting drugs across that blood-brain barrier is very, very difficult. So one of the attempts that they have to do that is to use this compound called L-DOPA, which to a limited extent they can get across there. And L-DOPA can be metabolized ultimately to make dopamine. Dopamine, interestingly, can be made into a hormone that we'll talk about a lot later called epinephrine. It's a hormone. And hormones are things that move in your body. They travel in your bloodstream. You probably know epinephrine better as adrenaline. Adrenaline is the flight or fright. When you get scared, your body makes adrenaline. And as we will see, we'll learn later in the class why adrenaline or epinephrine gives people these enormous bursts of strength. You hear about people that get scared and they go out and they pick up the end of a car, and you think those stories aren't true, and they're true. And they're true because of the way that this hormone works. We'll talk about that later in the term. Okay? So there's some other things made from amino acids. All right. Well, one of the things that we need to be thinking about with amino acids is ionization. We talked about Henderson-Hasselbalch, and with Henderson-Hasselbalch, you saw ionization because you saw gain and loss of a proton. Ionization, I'll remind you, involves gain or loss of a proton. So the amino acids have two groups that can gain and lose protons: carboxyl groups and amine groups. Remember that I said that every amino acid has an alpha carboxyl and every amino acid has an alpha amine. Every alpha carboxyl can gain or lose that proton. When it gains the proton, charge of 0. When it loses the proton, charge of -1. Okay? The amine, the alpha amine, when it gains a proton, charge of +1. When it loses that proton, charge of 0. I told you about 5 amino acids that have R groups that are either carboxyls or amines, and they too can gain or lose protons in exactly the way I talked about here. Carboxyls losing it, becoming charge 0, or becoming charge of -1, gaining it, having a charge of 0. Amines gaining it, having a charge of +1, losing it, having a charge of 0. So understanding how it is that amino acids gain and lose protons is important, and since you saw that Henderson-Hasselbalch really helped us to understand gain and loss of protons, Henderson-Hasselbalch is going to be critical for us to understand amino acids and their charges. All right, so let's think a little bit about that. Here's a simple amino acid. Schematically, it's shown here. There's the alpha carbon. There's the R group. There's the alpha carboxyl. And there's the alpha amine. It's a little upside down, but that's fine, okay? This one is shown, in fact, we can look at the structure down here. This one is shown with all of the protons on. If we were doing a titration curve, this would be at a very low pH. We would have all of the protons on. When we put all the protons onto an amino acid, the alpha carboxyl will have a proton on. The alpha amine will have a proton on. And if there are R groups there, they also will have protons on. This guy has an R group that doesn't have a proton on or off. We just call it an R. Okay? So for a simple amino acid, we have an alpha carboxyl and we have an alpha amine to consider. When the protons are on those, the overall charge of that molecule is a +1 because the carboxyl with a proton on has a charge of 0. The amine with a proton on has a charge of +1. If we add some sodium hydroxide to the solution and we raise the pH, we start seeing that curve going up, right? Everybody remember the titration curve I'm talking about? It rises rapidly, then it starts to flatten out, right? What's happening when it's flattening out? One word would suffice. Buffering. Buffering is going on, meaning resisting change in pH. And how is that buffering happening? We're starting to get a mix of salt and acid. Okay? There, on the left, is the acid. And there in the middle is the salt. How can I tell? They only differ by 1 proton, and the 1 proton they differ is right there. You can see the proton has started to come off. If I told you, and in fact you can see it right here, the pKa for the loss of that proton is 2.34. You don't need to memorize that. But there's the pKa of that carboxyl group. If I said we had a pH of 2.34, which of these forms would be present? Anybody? Both. That's exactly what I wanted to hear. Okay? At a pH of 2.34, I'm going to have half of everything present in the salt form and half of everything present in the acid form. You're exactly right. Half will be here, half will be here. Very good. Let's say I go to a pH of 4. what's going to be present? Mostly this guy. Now, here's where I'm going to give you a rule that's very helpful for you to estimate charge. Okay? A rule that's very easy to estimate charge. If the pH of a solution that I give you is more than 1 pH unit above the pKa, you may effectively assume that the proton is off. So when I gave you a pH of 4, that was more than 1 pH unit above 2.34, it tells you that that proton that was on over here is completely off for our purposes. On the other hand, if the pH of a solution is more than 1 unit below the pKa, you may assume that the proton is on. Now that's a rule, that estimate rule that I just gave you is not one I'm going to give you on an exam. You will need to know those two rules. I'll repeat them. pH more than 1 unit above the pKa, proton off. pH more than 1 unit below the pKa, proton on. Now you can use that rule for all kinds of things. You've already seen how you could use it here to tell that the proton was off and we had the middle form. How do I know I have the middle form? Because I've got another proton that can come off. Well, I apply the rule. pH of 4 is more than 1 unit below this pKa, which means that this proton associated with this pKa must be on. And which proton is that? It's this one right here. So at pH 4, I'm predominantly going to have this guy in the middle because it's more than 1 pH unit above the proton for this one and more than 1 pH unit below the proton for this one, and I'm set. What if I had a pH of 1? What do I have? I have a plus 1 because 1 is below the pKa of both of these guys. Both of these protons are going to be on, and I will have predominantly this species. If I had a pH of 12, I would have a charge of minus 1 because this proton would be off and this proton would be off. Make sense? This is great. I see a lot of nodding. Or people are saying, shut up, let's get out of here, right? It's great. This is very good. Makes sense? Questions about that? Yeah. Good question. So our question is, will the carboxyl always be the one that comes off first? The rule that you should have is that the pKa will always determine which one comes off. It turns out that the alpha carboxyl has the lowest pKa of all of the amino acids. Okay? Very good. We'll see the rule varies as we go through the R groups and so forth, but the alpha carboxyl will always have the lowest pKa value. Yes? Well, in the middle, yes and no. If I said 2.35, that's in the middle of those, but what would you tell me? It's not over a unit above that, right? So it's that 1 unit rule that's going to determine that, right? So if it were somewhere between 1 above and more than 1 below, then yes, that's right. Yes? Will the hydrogen on the alpha carbon ever react, meaning what?
Like how we're seeing like the protons are popping off of these compounds. Will the hydrogen on the alpha carbon ever become a proton?
So that's what's actually happened right here. It's come off as a proton.
But on the alpha carbon.
That is, oh, this, oh, I'm sorry, on the alpha carbon, I'm thinking the alpha carboxyl. No, you will not see that come off.
Okay.
No, no. Good question, yeah. Only carboxyls and amines. There are, in fact, I'm simplifying things for you. It turns out that sulfhydryls can lose protons, but that becomes another thing that you have to memorize, and I decided not to make you memorize it. Tyrosine can lose a proton off of its hydroxyl, and I decided to not make you memorize that. So that's a couple places where it's a little bit more complex. This will not come off, though. Yeah. Okay, very good. Very good. All right, so let's look at a more complicated one. That's a simple one. Let's look at a more complicated one. All right? Here's histidine. Histidine is one of the basic amino acids. You're seeing its structure here for the first time. You don't need to memorize its structure. But suffice it to say that its structure has an amine group. Okay? That amine group is right there. And when this nitrogen gains that proton, it has a plus charge. If we start with histidine at pH 1, okay, if we start, let's make it less than 1 because that's a pKa of 1.82. Let's say we've got histidine at a pH of 0.5. What's going to happen? Well, 0.5 is going to be more than 1 pH unit below all of the pKa's, right? Because you can see them all on the screen right there. That's going to mean that every proton is going to be on. Well, once you get used to doing these, you see this is actually very simple to do. Proton on the R group is an amine, therefore it will have a plus charge. Proton on the carboxyl, you put a proton on a carboxyl, you get a 0 charge. You put a proton on the alpha amine, you get a plus charge. So that's how we get a +2 charge starting over here. At one point, a pH of 1.82, we will have exactly equal amounts of +2 and +1. If we get up here to a pH of 3, then we're going to predominantly have this guy right here, right? pH of 6, we're going to have equal amounts of these two. pH of 8, we're going to have predominantly this guy, okay, etc. You can see what's going on. So even though it's more complicated, it's not overly complicated. You could figure this out from the rules. All right? So if I gave you this on an exam and I wanted you to predict charges for me, I would say something like the following. Assume in this protein, or in this amino acid, in this case, that the alpha carboxyl, I can't even say it right now myself. The alpha carboxyl has a pKa of 2. It's a good estimate. Assume that the R group for amines has a pKa of, let's say, 12. And assume that the alpha amine has a pKa of 9. This one's a little bit different, I understand. But if I gave you that, you could make this prediction based on that. So you're not going to need to memorize any pKa values. I will give them to you very much like I just gave them to you here. Make sense? And then you would look at this and say, okay, now I just apply the rules for the pH he's given me. I can tell the charge, et cetera, et cetera. Now I see some frowns. When I see frowns, I always want questions, but nobody ever gives me questions when they frown. You weren't frowning, but I'll take your question. Go ahead.
Also, the pKa values are the values for each of those groups.
That's right. The pKa values are always associated with ionization of a specific group. That's correct. Okay. Let's see. Where are we at here? Here's a table of pKa values, blah, blah. You can see that largely alpha carboxyls are around 2. Alpha amines are around 9. And R groups vary depending upon the particular R group that we're talking about. But I'll keep it simple for you on an exam. All right. Let's turn our attention, actually, let's see here, titrating. Remember I described titration to you, and I said if we had something that had two different groups that could ionize, and each one had a different pKa, we would see 2 flattenings. And now you see it. Pretty cool. Now you see it. I'm going to give you a definition, but I'm not going to make you calculate how to do it because I find it ends up being kind of a pain for students. Okay? But a definition that I definitely think that you should know. It's actually on this thing right here. It's called the PI. The PI is a very specific pH. The pi is the pH at which a molecule has a charge of exactly 0. The pi is the pH at which a molecule has a charge of exactly 0. Now, even though it looked like we could predict where the charge would be 0, that prediction was over a range. Okay? So I'm not going to make you calculate the exact the exact pi of a protein, but you should know what the pi is. So it's the pH, it's a very specific pH, and it's a specific pH where the molecule has a charge of exactly 0. Well, here we see the titration of a simple amino acid. The simple amino acid has carboxyl with the proton on, carboxyl with the proton off, and we're going to have half and half of those at the pKa of that carboxyl. Up here, we've got the amine with half of the proton on, half the proton off, and that's going to happen at the pKa of that amine group. You could look at this graph, and I said, okay, pH of 1, what you're going to have, you would say, well, 1, more than 1 unit below the pKa, proton's going to be on. And remember the other rule I gave you about 1 pH unit? Anybody remember what it was? I gave you a rule about 1 pH unit in the last lecture. The first person to tell me gets 2 points on the next exam. What about it? Say it again. That's what I'm looking for. She beat you to it. Okay. So the buffering range is 1 pH unit below to 1 pH unit above. So that estimate I just gave you corresponds to the buffering range. Okay. So run me later what your name is, and I'll give you 2 points on the exam. Okay? All right. Okay. So that's what this looks like. That's what this looks like. All right? If I had histidine, what do you suppose histidine's curve would look like? It would have 3 of these flattening regions, right? It's exactly what it would look like. Okay. Well, amino acids make up proteins. I'm going to introduce the topic of proteins here, and then I'm going to finish with a song. Okay? The topic of proteins. Proteins, as I said earlier in the lecture, are polymers of amino acids. They're made by joining one amino acid to another amino acid to another amino acid to another amino acid. This happens in structures we call the ribosome. Our cells have little structures, and you don't need to write that down now. We'll talk about that later. But they have structures called ribosomes that make that linkage between individual amino acids. The linkage between amino acids is known as a peptide bond. I mentioned that to you earlier. And a peptide bond happens as a result, not a very good structure there, sorry, of a reaction that looks like this. Peptide bonds form between the alpha carboxyl of one amino acid and the alpha amine of another. I'll repeat that because that's very important. Peptide bonds form between the alpha carboxyl of one amino acid and the alpha amine of another amino acid. When those get joined, they make up what's called a peptide bond. The peptide bond is shown right here at the very bottom of the figure. The formation of the bond results in the loss of water. And if we want to make the reaction go backwards, that is to break the peptide bond, we have to add water to it. And there are enzymes that will do that. Enzymes called proteases will break peptide bonds. I showed you 2 of them the other day. Trypsin and pepsin. What those guys do is they break peptide bonds, and they break by adding water to that bond. Okay. Now, peptide bonds actually give you very good simplification, actually. It looks like they're complicated, but they actually give you simplification when it comes to determining charge. Now, I'm not going to have a chance to go into that today. I'll talk about it on Monday, but I will just throw that out there for you, that they give you simplification in terms of charge. How? Well, there was the original carboxyl group. There was the original amine group. After you've put it together into a peptide bond, neither one of them can gain or lose a proton. So peptide bonds are everything that's in the middle of this guy. None of these guys can have gain or loss of a proton by the alpha carboxyl or by the alpha amine. It means that on the internal part of this protein, the only things that can be charged are the R groups. So when I go to calculate the charge of a protein, I have to know the alpha amine, which is still able to ionize. I have to know the alpha carboxyl. And then I simply have to look and say, well, can this one ionize? Can this one ionize? Can this one ionize? Et cetera, et cetera. Makes sense? I just noticed it says R6. I don't know why that says R6. I should say R3. Okay, I'll get that changed. All right, but now, so we can schematically write what's called a polypeptide. And by the way, people talk about proteins and polypeptides, and technically they have different meanings, but I use those two terms interchangeably. Polypeptides and proteins, I use the terms interchangeably. Okay? A polypeptide means it has multiple peptide bonds, which is what a protein has. Right? You'll notice the way that we can schematically write this. Here's amino acid number 1 on the left, followed by amino acid number 2, amino acid number 3, although it has a 6 on it, amino acid number 4, amino acid number 5, etc. All right? As we look at this, we see R group down, R group up, R group down, R group up, R group down, R group up. That's not just written for convenience, but it turns out that that's the way that the R groups tend to arrange themselves in a polypeptide chain. And that becomes important, especially if the R group is large. Becomes especially important if the R group is large. Okay? So R groups, we start to see, have an effect on the overall structure of a protein. Okay. That is what I want to say here today. Any questions on what I've just said? You guys want to sing a song? Okay. There's an old Woody Guthrie song I'm very fond of called This Land Is Your Land. Anybody know that song? This land is your land, this land is my land. Da 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 da. This one's called, this song's for BB350. It's 1 o'clock and Ahern's talking, Henderson and Hasselbach and PKAs and buffers I should know. This song's for BB350. I hope that maybe he'll think the way we wrote our answers wasn't crazy. I really need the partial credit, so this song's for BB350. It's really groovy that it improves me watching lectures and QuickTime movies. I really need to go and download those podcasts for BB350. I'm feeling manic, I'm in a panic. I'd better study my old organic. It has reactions that I need to know. This song's for BB350. I know he said it, that's why I dread it, 'cause I skipped Friday's extra credit. 'Twill probably haunt me, that lowly zero grade in BB350. It could be steric or esoteric, that carbons get so anomeric. I'm too hysteric, better let it go. This song's for BB350. Have fun this weekend.